and welcome to this video, which is my second video in the Design EAD project. This is a repeat of the presentation I did for the EuroSOI ULEZ 2021 conference, which is a presentation of the article titled Impact of Different Types of Planar Defects on Current Transport in Indium Phosphide. So let's get to it. In the Design EAD project, we're working with III-V materials. And the reason we're doing this is because III-V has a number of interesting and unique properties, such as high carrier mobilities, direct and tunable band gaps in the entire optical spectrum, and low exciton binding energies. These properties can be used for stuff such as improving current MOSFETs and CMOSs, to improve pin photodiodes, or even to enable entirely new optical devices, such as lasing microdiscs or topological photonics. When integrating III-Vs into silicon, into the current silicon platform, there will be a number of defects occurring, which will degrade performance. This is why the Design EAD project is an investigation of defects in III-Vs. And specifically this work, I'm looking at planar defects in indium phosphide. The two kinds of planar defects that I'm investigating, the first one of them is seen here on the left, which is called a rotational twin plane, RTP. An RTP is basically a rotation of the lattice by 60 degrees around the 111 direction. And the resulting lattice looks like a mirror image of the other lattice with the atomic species swapped, which is what you see here on the left. The other kind of defect that I'm investigating is so-called stacking faults. So indium phosphide crystallizes in the zinc blende lattice structure. And from the 111 direction, this has an ABC stacking sequence. This stacking sequence can be interrupted in one of two ways. You can either have an added layer, which yields an extrinsic stacking fault, or a removed layer, which yields an intrinsic stacking fault. Now, the way you investigate planar defects in III-Vs is by high-resolution STM images taken from the 110 direction, because this allows vision of the stacking in the 111 directions. This is what you can see on the right over here, where the first image on the left of these is clearly two RTPs, because the lattice changes direction by about 60 degrees at the defect. On the image on the right, though, it's not clear what kind of defect is appearing. This is because in indium phosphide, the indium atom is much larger than the phosphor, which makes it really hard to see where the phosphor atom is. And without knowing exactly where the phosphor atom is, an intrinsic stacking fault looks exactly like two RTPs just back to back. So this is why I'm investigating both RTPs and stacking fault in this work. Specifically, I'm actually looking at 6 kinds of systems, one of each stacking fault, one system with a single RTP, another system with 2 RTPs separated by 10 layers, so kind of like the image on the left, just further apart, and finally one with 2 RTPs just back to back. The 6th and final system is just a reference system of pure indium phosphide in the zinc blende structure. Now, the way that I'm investigating these systems is by using the state-of-the-art simulation software Quantum ADK from Synopsys to employ the first principle methods density functional theory with the PBES functional, which is a generalized gradient approximation functional. I combine this with non-equilibrium green functions to simulate transport properties as well as finite bias. My simulation started with a relaxation of the simple unit cell, which yielded a lattice constant of 5.89 angstrom, quite close to the experimental value, kind of validating my choice of parameters. I then repeated my system in the 111 direction until my system was 149 angstrom wide. My resulting system were then 4 angstrom in the transverse directions, but because I employ periodic boundary conditions in these directions, my system is technically semi-infinite, with the only non-infinite part being the 149 angstrom wide transport region. So this is all bulk simulations. After these 149 angstrom, I had my electrodes, which in these simulations were pristine indium phosphide, not metals. So I don't have any metal semiconductor contact and therefore no Schottky barriers in my simulations. Finally, I added a background N-type doping of 10 to the power of 17 per cubic centimeter, which is kind of in line with what is achieved experimentally. Now onwards to the results. The first result I'm going to show you is the Hartree difference potential. This is basically the electrostatic potential, so the solution of the Poisson equation, except that we subtract the doping density from the total overall electron density. Now I told you I had 6 systems, but I'm only showing you 2 of them here. This is because the 2 different stacking faults were quite similar, and all the different RTP systems were also really similar, but there's a big difference between the 2 of them. So in these simulations, or in these graphs, I'm showing you the envelope outlined in red. This is just because it makes it easier to see the perturbance caused by the defect. The actual potential is actually what you see in between the envelopes, which is highly periodic, with a periodicity corresponding to each atomic layer in my simulation system. When you look at these, you see that the RTP only causes a small perturbance in the potential, and we therefore don't expect a big difference in electrical properties from this kind of defect. On the other hand, the stacking fault caused a huge potential barrier to form, which should severely hinder electron transport across this direction. To further investigate this, we calculated something called the specific contact resistance, which is calculated as the difference in resistance from the central region to the electrodes, which is calculated from the conductance, which is again calculated from the transmission spectrum in the usual fashion. Now we did this for a number of dopings, so corresponding to Fermi level shifts. So 0 on this axis corresponds to the background N-type doping of 10 to the power of 17 I mentioned earlier, while 0.17 out here, or minus 0.24 out here, corresponds to a high N or P-type doping of 6 times 10 to the power of 19 per cubic centimeter. Now, what we see in this graph is that for intermediate doping levels, all the RTP systems has a small increase in resistance compared to the pristine single-end system by about 3 times higher resistance, whereas the stacking faults have several orders of magnitude higher resistance, with the extrinsic SF being about 4 times higher than the intrinsic SF. This difference is constant throughout the intermediate doping range, but for very high P-type doping out here, something interesting starts to happen. The difference between the 2 kinds of stacking faults starts to decrease, and we start seeing a difference between the different kinds of RTP systems, and they actually get closer to the stacking fault system. Now, while this high P-type region is definitely interesting, this work was more interested in the intermediate doping levels, so our continued investigation happened at the 0 Fermi level shift, so the background N-type doping. The next step in my investigation was to add a bias to the system and try to actually run a current through it. The resulting IV characteristics can be seen here. And kind of as expected, we don't see any decrease in the current from any of the RTP systems. At least the difference between the RTPs and the pristine system is within numerical accuracies, so we can't really say anything. The stacking fault, on the other hand, strongly dampen out the current, with the extrinsic SF damping out the current more, especially for low voltages. Interestingly, the intrinsic SF starts to damp out current more, around 0.2 volts, but they are both approaching all the other systems when the voltage is high enough that the potential barriers can be overcome. While we couldn't actually converge the results beyond 0.3 volts, despite our greatest efforts, we expect that they would reach the RTP systems, especially at around the breakdown voltage, which in this simulation was found to be 0.6 volt. This corresponds to the band gap of 6 eV, or 0.6 eV. which is of course far from the experimental value of about 1. But this is normal for DFT simulations, which always strongly underestimates the band gap. The electrical properties above and below the breakdown voltage is still expected to hold. It's just the value itself that shouldn't be taken seriously. To further investigate why these stacking faults dampen out current so much, especially for the low voltages, we calculated something called the projected local density of states. This is similar to what you might know as a band diagram. In fact, we've even shown the conduction band edge and the valence band edge in yellow, which is calculated automatically, which is why we have these fluctuations shown in these images. I didn't have high enough sampling in my calculations, so just disregard that. The difference from this and a band diagram is that we show the amount of states, the density of states, shown by the color. So we kind of see here why the RTPs don't block out any current, because there's no real difference in the density of states. There's a slight relocation of states in the high energies and the low energies, but nothing really close to the conduction and valence band edges. So that's why we don't really see a difference in the current. For the extrinsic and intrinsic SF though, the states congregate close to the defect, leaving areas around it which are highly void of states to conduct current. Especially the extrinsic SF has a lot of defects in the band gap, a lot of trap levels. Actually, it even has so many of them that it almost becomes metallic at the defect. But because the states are still removed around it, the current is still strongly dampened. The final investigation we did is a calculation of the formation energies compared to the pristine indium phosphide. And luckily here we found that both SF has a huge formation energy of 1/2 or 1 eV, which means they'll never really form. The RTP, on the other hand, have a very small formation energy, which means small thermal fluctuations can cause it to form. And we even found that the two systems with 2 RTPs have a negative formation energy, suggesting that the true ground state of indium phosphide could be a twinning superlattice. We would need more investigation into this to say any conclusive about that though. But we can still conclude that while the twin planes are very, very likely to form during growth, they show little to no effect on current transport, at least along the 111 direction. Whereas the stacking faults, while they have a huge detrimental effect on the current transport, they're also very unlikely to form during growth. And that's my conclusions. These are the references I showed you. And we have to thank the Binning and Rohrer Nanotechnology Center, as well as the RT West supercomputer. And finally, we were funded by EU. And this was the presentation that I gave for EuroSOI, ULIS. If you want any more details on this, look at the paper. That'll be hopefully published soon. Otherwise, send me an email. Thanks you all for watching, and I'll see you next time. Bye.